Please let me introduce myself to you. My name is Diego Magallanes. We want to thank the ACEX 2025 for this opportunity to present our paper, Vibration Analysis of Gears Obtained by 3D Printing a Lattice Structure Topology Optimization Method. This work was supported by the Instituto Politécnico Nacional. The evaluation of the dynamic response of a spur gear optimized size and manufactured in various polymers is discussed in this article. Incorporation of new techniques in structural optimization methods applied to the design in combination with the introduction of additive manufacturing in mechanical components has focused on improved performance, increasing durability and reliability, and reduced cost. Some optimization methods can be oriented in reducing stress concentrations, weight, stiffness, noise, etc. Topological optimization has contributed greatly to the reduction of mass in the manufacturing of various elements for different areas or industries. This is by means of additive manufacturing such as fused deposition modeling 3D printing. However, this alters their mass and stiffness, which modifies their natural frequencies and mold shapes. The methodology proposed in this paper is shown in Figure 1. First, it was estimated the natural frequencies of a solid spur gear by a structural analysis using the finite element method. 4 different materials were considered for this first evaluation, which are PLA, PETG, ABS, and PLA-CF. The mechanical properties are listed in Table 1. These results are contemplated as a reference point for the future comparisons of results. Then, a topological optimization based on lattice structure was applied to the original spur gear. The objective of this optimization is a reduction in mass in the hub area of the spur gear. This was targeted in a 30% reduction. The lattice structure applied to the hub area produced a 3D model geometry that was used in the numerical evaluation of the optimization process. This methodology was then replicated for each change in material in the new model. The transmission load considered in the evaluation was 632.1 Newton, and a fixed support was applied in the shaft zone of the spur gear. Natural frequencies and mold shapes of a spur gear of 20 feet were obtained by numerical evaluation. Figure 2 shows the comparison between the original and optimized model. It is noticed that a considerable reduction in the natural frequencies is achieved when a reduction in mass is applied. When different materials are evaluated, a major difference in the natural frequencies is noted when a PLA with carbon fiber is used. An almost linear increase in the natural frequencies is perceived in dynamic behavior. A variation around of 61 to 65% is computed in the first 4 materials, presented in Table 1. In the case of PLA with carbon fiber, a variation of around 76% is calculated. This paper presents the result of a dynamic evaluation of a spur gear made from various polymeric materials, including PLA, PETG, ABS, and PLA-CF. This was achieved by determining the component's natural frequencies and mold shapes, and examining its response to external excitation forces using a response spectrum. Further experimental evaluations are required to validate the results presented in these jobs. Finally, I want to thank you for your kind attention. At the same time, I send my best regards from Pachuca, which is a lovely place in Mexico, and it is close to the campus of my university.
Es que nunca olvidarás.